The liquid hydrogen leak didn't just happen once. It keeps coming back. Even after previous fixes and reinforced seals, Artemis II is still battling hydrogen escaping during fueling tests. And now, it's starting to look less like a one-off issue and more like a stubborn engineering challenge. That's no longer just a delay headline. It raises a harder question. Why does this keep happening? And what does it mean for the rocket meant to carry humans around the moon? Could this persistent hydrogen leak reveal something deeper about Artemis II's long-term destiny? The key development here isn't that a leak was found, it's how it was found and what that detection tells us. During Artemis II's wet dress rehearsal at Kennedy Space Center, NASA fully loaded the Space Launch System with super cold liquid hydrogen and oxygen, simulating an actual launch countdown. This is not a symbolic test. It is the moment when the rocket experiences the exact cryogenic stress it will face on launch day. And that's when hydrogen sensors began detecting abnormal readings near a quick disconnect interface, the same general area that has challenged engineers before. NASA immediately halted fueling operations. That decision alone tells you something important. The monitoring systems worked exactly as designed. Hydrogen is invisible, odorless, and highly volatile. It cannot be seen leaking. It is detected through pressure changes, gas concentration monitors, and thermal fluctuations. Engineers analyzed flow rates, valve performance, and temperature behavior to isolate the source. Early briefings indicated the leak likely occurred at the interface between ground fueling hardware and the rocket's core stage, one of the most delicate connection points in the entire system. Now here's why this matters. Liquid hydrogen must be stored at around -253 degrees Celsius. At that temperature, metal contracts, seals stiffen, and microscopic imperfections can widen just enough for hydrogen, the smallest molecule in the universe, to escape. Even reinforced seals from previous Artemis I upgrades can behave differently under slightly altered pressure conditions. Hydrogen doesn't forgive assumptions. But this wasn't a catastrophic failure. It was a detection under controlled rehearsal conditions. The system identified irregular readings before ignition. That distinction is crucial. Artemis II wasn't stopped mid-launch. It was paused before risk escalated. The leak forced a delay, yes, but it also validated NASA's safety architecture. Still, when a problem reappears after redesign efforts, curiosity naturally grows. If the leak is manageable, why does it keep resurfacing? And more importantly, does this reflect hydrogen's difficult nature or something more systemic inside SLS itself? That's where the conversation shifts from mechanics to momentum. The delay into at least March is not just about repair time. It intersects with the larger Artemis roadmap. Artemis II is the mission that proves NASA can safely send humans beyond low Earth orbit again. It carries 4 astronauts on a free return trajectory around the moon, validating life support systems, propulsion coordination, navigation precision, and deep space communication. This is the bridge mission. Without it, the lunar landing of Artemis III cannot move forward. NASA officials have emphasized that safety drives every timeline decision. When hydrogen readings moved outside acceptable thresholds, the mission window automatically shifted. Engineers will now roll the rocket back, inspect the affected interface, replace or reseal components if necessary, and repeat fueling tests before approving flight. That process takes time, not because it is chaotic, but because it is methodical. However, expectations surrounding Artemis are enormous. This is not just a technical program. It represents a strategic and symbolic return to deep space. Schedules have already adjusted in previous years, due to hardware readiness and system integration complexity. Each new delay, even a short one, adds weight to the public narrative. Is this just routine engineering refinement? Or are we seeing cumulative pressure build? The answer may be more nuanced than headlines suggest. Hydrogen-fueled heavy-lift rockets have historically faced similar challenges. The Space Shuttle dealt with hydrogen leaks at external tank interfaces. Cryogenic propellant systems are powerful but unforgiving. The difference now is visibility. Every Artemis milestone unfolds in real time under global scrutiny. What makes this moment important is not that Artemis II moved by weeks, it's that this mission carries astronauts. Human rating a rocket changes the threshold. When no crew is aboard, engineers accept certain tolerances. When people are sitting inside Orion, margins tighten dramatically. So what appears externally as hesitation may internally represent discipline. Still, a pattern forces an uncomfortable question. If hydrogen remains such a persistent challenge, what does that imply about SLS as a long-term backbone for lunar exploration? The Space Launch System was designed for one primary purpose: sending heavy payloads and crews beyond Earth's orbit. It delivers immense thrust by burning liquid hydrogen and oxygen in its core stage engines. That performance advantage comes with complexity. Hydrogen's extreme cold and molecular size make it efficient, but also notoriously difficult to contain. After Artemis I, NASA replaced and reinforced quick disconnect seals to prevent recurrence of earlier leakage. For Artemis II, engineers believe the system was fully validated. Yet under new fueling conditions, hydrogen readings again indicated escape at a connection point. That doesn't necessarily mean the redesign failed. It may reveal how cryogenic systems behave differently over time, under varying pressure sequences, or during extended countdown simulations. Here's what's important. NASA's testing philosophy assumes that hardware will behave unpredictably under real-world stress. That is precisely why wet dress rehearsals exist. They are not ceremonial. They are brutal stress simulations. When hydrogen leaks during this stage, it exposes a vulnerability before launch. That is not weakness. That is engineering transparency. But SLS is not a rapid reuse rocket. It is an expendable heavy lift system, built for precision missions rather than high-frequency launches. Each fueling operation is a critical event. There's little room for iteration once hardware reaches the pad. That increases the psychological impact of any anomaly. So is SLS under structural pressure? Perhaps not in the way some assume. Hydrogen systems are inherently demanding. The Saturn V faced cryogenic management hurdles. The shuttle encountered seal-related hydrogen issues throughout its history. Artemis II may simply be walking the same path of refinement that every large hydrogen rocket has walked before. What feels different now is timing. Artemis represents humanity's return to deep space after decades. Expectations are elevated, tolerance for visible setbacks is low. Yet what we are witnessing may not be fragility. It may be the unavoidable friction of high-performance propulsion, meeting uncompromising physics. And that leads us to the bigger lesson. The recurring hydrogen leak does not signal collapse. It signals caution. Artemis II was paused because sensors detected something that didn't align with safety margins, exactly as they were designed to do. That means NASA's monitoring architecture is functioning. Deep space missions are not defined by smooth countdowns. They're defined by relentless verification. When humans travel around the moon for the first time in more than 50 years, no valve, no seal, and no cryogenic interface can operate on optimism alone. So maybe the real story isn't about a leak that keeps returning. Maybe it's about a program that refuses to ignore it. So what do you think? Do you see this as normal engineering refinement, or a sign that Artemis still has bigger hurdles ahead? Drop your thoughts in the comments. I'm genuinely curious where you stand. If you enjoyed this video, don't forget to like, share, and subscribe for more updates on space exploration and scientific discoveries. Your support truly makes a difference and helps this channel grow. Thank you for watching, and see you next time.